Gerald, we have to start by at least 3:10, correct?
Yes, sir. Yes, sir.
Please start
Yes, sir. Just 2 minutes,
as
sir.
soon as possible, okay?
Participants,
So
sir.
that
Yes, sir. Yes,
we
sir.
can
Yes.
take 1 hour time.
Okay, sir. No, you
Okay.
can start, sir.
And also you can instruct, you can stop me. Suppose if there is a problem in changing the slide, I am more changing the slide, okay?
Okay,
And
sir. Okay, sir.
if there is any problem in audio or video, please stop me, okay?
Yeah, sure, sir. Okay, sir. Okay, sir.
Okay.
Okay. Okay. Sir, shall we start now, sir?
Yeah, please.
Uh, so, good afternoon to everyone. On behalf of Ramco Institute of Technology, Department of Mechanical Engineering, RITMECCAD Center, and IEE. So, we are hosting the day 9, a short-term course on finite element analysis, session 2. So, this session is handled by Dr.A.Vasanthanathan, sir, Associate Professor, Mechanical Department, Mepco Engineering College, Sivakasi. Sir actually, I am a student of sir. Actually, I have studied finite element analysis under him. Based on his inspirational teaching only, I am hosting this kind of courses, and also I am taking finite element analysis. So I am very proud of him. So now I invite Dr. V. Sokumar, sir, Associate Professor, Department of Mechanical Engineering, Ramco Institute of Technology, to introduce our resource person for this session. Welcome, sir.
Thank you, Mr. Gerald John Beto. It's my immense pleasure to share a few things about our today's chief guest in this forum. First of all, I welcome Dr.A.Vasanthanathan, sir.
Thank you, sir. Thank you.
In the year 1990, sir completed his UG degree from MK University, and sir pursued his ME from IIT Madras in the year 2004, and sir completed his PhD in the year 2014 from Anna University. So he is having a vast experience, total 16 years experience in teaching, including industry experiences 2 years, and the total research experience is around 12 years. Now sir guiding around 6 PhD scholars and guided 22 UG projects and then 16 PG projects. He published a pattern around 5. List of his research project is completed a project in the field of composite structure. As a principal investigator, he received the grant of 8.6 lakh. He's acquired competencies in core finite element analysis, advanced composite materials and structures, advanced mechanics, elasticity and strength of materials standard, materials for analysis and simulation standard as a professional simulation engineer, issued by NAFAMS UK for a period of 3 years from 2020. So his field of interest is aircraft structures, space structures, FEA, and all other. And his programming language sir is well versed in MATLAB, and he published around 21 international journals and 22 international conferences, and he published one book chapter also. He received a lot of research, recent external excellence what he achieved. He
Shivkumar,
received more
I think
awards.
it's enough. I think, Shivkumar. Thank you anyway.
Yes, sir. And
Already
many
we
more.
are running out of time, but anyway, thank you very much for your introduction.
Okay.
May I start now?
Yes. This is
Yeah.
it shows his simplicity. Thank you, sir. Thank you for this
Thank you. Thank you.
your time constraint. Okay, thank you very
Okay.
much. I am very proud to introduce such kind of simple person to this
Yes.
forum.
Yes.
Welcome, sir. You please share the dice. Thank you, sir.
Thank you, Mr. Shivkumar and Gerald, for your wonderful introduction. At the outset, I would like to thank the head of the institution, Dr. Rajapalayam sir, and all the faculty of Mechanical Engineering Department of Ramco Technology for having invited me to deliver a lecture on the topic in the field of finite element analysis. I think it's a wonderful opportunity for both student community and faculties to gain the knowledge in the field of finite element analysis in this lockdown period. The time allotted for me is 1 hour. If possible, may I take some 10 or 15 more minutes, if possible, Gerald?
Yes, sir. Yes, sir.
Yeah, okay. We will see. Okay, we will see. So
Yes,
I
sir.
just want to share my experience in the field of finite element analysis with all the students and faculty. The topic selected is convergence and plane problem in finite element analysis. Suppose if you select FEA as your tool, numerical tool for solving any problem using packages, so-called ANSYS, LSDyna or COMSOL, Abacus, there are wide opportunities. So before you get into the software, you need to do some groundwork. Okay, that's what I'm going to speak today. So directly you should not go and sit in the software GI. Before that, you have to make some groundwork. You have to identify what is the type of problem, whether it's coming under 3D or it is coming under 2D. So today's topic is plane problem. So plane problem is nothing but it's a 2D problem. Okay, the moment you talk about plane, the dimension of your problem becomes 2D, correct? So two-dimension problem, or else if you are solving as one-dimension problem, so it is not that you have to construct the real 3D model for solving. So even in this title slide, you are seeing a dam structure, correct? So if you want to solve, if you want to analyze this dam using finite element analysis, it is not that you have to draw a three-dimensional model of the dam. Even you can convert it into 2D using some concepts. So that concept is coming under this plane problems. I think my audio is okay, correct?
Yes, sir. It's okay, sir.
Okay. Thank you. So, and convergence, the moment you talk about any finite element analysis, convergence is coming into the picture. Okay. So these two topics are very much useful for engineers to carry out any type of finite element analysis so that you can simplify your results. You can save your computational time. Even you can go for publication in the field of finite element analysis. Okay. So this is how I am planning my presentation today. We'll start with convergence. We discuss what is plane problem, what are the types of plane problems like plane stress, plane strain, axisymmetry. Apart from these three, we will see what are all the various types of symmetry. You know that if you climb for symmetry, what you can do is you can simplify your problem. Okay. So whenever you solve analysis, you have to always try to simplify your problem. So from 3D to 2D or 3D to 1D, or why not 3D to one dimension. Whenever you solve a beam problem, you can it is possible for you to convert a 3D into one dimension. You can simply draw a straight line and say that is a beam, and you can incorporate sectional properties, material properties. That is allowed. So what type of symmetry, if you study, if you see that any particular symmetry is existing in your domain, you can go for simplifications. Okay. And if time permits, we will discuss about the constitutive law, that is the stress strain equation for two dimension. Okay. Yes. So convergence in FEM. So normally we select finite element analysis for solving complex problems. Okay. So for simple problems, we can depend on the results in books or journals. You say you are working with only a simple cantilever beam or a simply supported beam. You have the exact solution in your strength of material book itself. Okay. But the moment you talk about any complex material, complex structures, so you are seeing two complex structures here. Okay. It is a landing gear of an aircraft. Okay. So this is the so Gerald, whether the model is visible?
Yes, sir. It's visible, sir. Visible, sir.
Okay. So this is the landing gear. I think you are able to see the landing gear here. Okay. The landing gear is kept below the wing. Okay. So in aircraft, the wing is a very critical part. Okay. Actually, you have a landing gear. At the time of takeoff, this landing gear will come out. And after takeoff, what happens? This landing gear will go inside a wing box. This is a wing box actually. And you know that this wing contains the engine here. You have the fuel tank here. You have the fuel tank. You have the flapping device. Okay, you have the flapping device here. So it's if you consider the wing itself, it's a very critical part. So before fabricating a wing, definitely finite element analysis is required. Okay. So for, and it's a very massive structure. It's a very longest structure actually. So in an aircraft, the first longest structure is the fuselage. The first longest structure is the fuselage. The second largest structure is the wing. Okay. So for meshing a wing, okay, how do I, so, and I assume that the audience are having the basic fundamental knowledge in FEM. Okay, correct. So I am not talking about the ABCD of finite element analysis, but I am talking about the application, okay, and the basic concepts. How do we convert 3D into 2D? Okay, so as the participants are having the basic knowledge in FEM, now this convergence is very easy for you to understand. So I want to have the optimal size of this aircraft wing structure. How do I find it? So this is the situation. This situation will occur for everyone whenever you solve a problem in FEA. So the researchers, whoever doing PhD, I advise you to use finite element analysis as your numerical tool. Using this, even you can publish one paper out of it. So suppose if you are planning for a paper in finite element analysis, in your paper, you have to definitely write a chapter about convergence, verification, and validation. Now comes what is the meaning of this convergence. Identifying the optimal size of the element is so-called convergence. Okay, are you able to understand? Now I need to find the optimal size of the element. It is not that if you use fine mesh, you know the meaning of coarse mesh and fine mesh, correct? Suppose let's say example, I use a fine mesh for the entire wing, okay, or the entire fuselage. So this is the fuselage, very long composite cylindrical tube, okay. I am using a fine mesh for the throughout the fuselage or throughout the aircraft wing. You just think about the computation time. Your computation time will be very longer. Okay, that's not the correct procedure. Also, if you use a coarse mesh, so if you're telling that I want to reduce the computational time, so I am using the coarse mesh, okay, instead of fine mesh. That is also wrong. If you are using the coarse mesh throughout the entire domain, there will not be any accuracy in your results. So keeping these views in consideration, I have to find the optimal size. If you select an optimal size, your computational time will be optimal without losing your results. Okay, now you see the graph. Okay, the x-axis is number of elements, the y-axis is any field. It is displacement. Okay, if you are working with thermal problem, temperature will be the y-axis. If you are working with fluid problem, you can consider pressure or velocity, something like that. Okay, correct? This horizontal line is the exact solution. Exact solution is nothing but known solution. Okay, or you can also consider this as your experimental solution, your experimental results. Okay, now you start your finite element mesh from mesh coarse mesh. If coarse mesh, the number of element will be less. Now I am slowly increasing the number of element. Now I am slowly increase the number of element. That is, I am slowly moving from coarse mesh to fine mesh. Okay, so your results are improving. Your results are improving. You see this point actually. Okay, this point is called convergence. At this point, convergence occurs. So beyond this point, what happens? The curve becomes flattened, correct? If it is flattened, what is the meaning? Even though your number of elements are increasing, your results are not improving. So that point is called optimal size of element or optimal number of element. If you are able to predict this point, your computational time will be greatly saved. Okay, correct? So you can stop your analysis here. Okay, it's not that if these points are not at all required, because that gives the same results. So n naught, if I know the value of n naught, I will take n naught as my mesh size or number of element, and I will complete my analysis. Okay, so this is called the convergence curve. This is very important whenever you write a paper. Okay, I am showing an example here. I am showing an example. So this is my own paper. Okay, so you just see here. I have an experimental result. Okay, I have an experimental result. So you can plot it here. Okay, this, let's say example, this is the experimental result. Okay, then these are the mesh size in my analysis. I start with 3.8. Then slowly I am moving from coarse to fine. Okay, so I got a result with the 2 millimeter mesh size. Then I reduce it further to 1.8 or 1.6, something like that. Okay, these values are not at all changing. I infer that this you have to record it actually. You have to experience this in ANSYS results. If you see that your ANSYS results are not improving beyond certain size of the element, that is called optimal size of the element and convergence has occurred. Okay, based upon that, you have to write your analysis, conclude your analysis. This is just for an example. I am showing the convergence study. Even in your thesis, if you are a PhD scholar, in your thesis, finite element analysis should be a main chapter and subchapter should be a convergence study. If you are writing a paper, FEA should be a chapter in your paper and convergence study is a subchapter. Okay, right. So now we are slowly moving to plane problems in elasticity. So now having known the concept of convergence, okay, now somewhat you are familiar with convergence. Okay, now you come to this plane problems. Okay, so any complex structure, okay, actually you consider any complex structure, it is a real 3D structure. Okay, it may be a aircraft structure, or you consider a rocket structure. This is a rocket, it's a model of a rocket launch vehicle. This is a model. Okay, so this is also a complicated 3D structure. Okay, now before I start my modeling work, I have to check whether any chances are there for converting the 3 dimension into 2 dimension or 3 dimension to 1 dimension. Correct? That is called plane problem. So plane problems, there are 3 opportunities for you. One is plane stress, plane strain, and axis symmetry. Okay, most of the structure will have these assumptions. Okay, we will see one by one. If you see that your complex structure comes under any one of these 3 category, then you can convert your 3D model into 2D model. So you just think about modeling a 2D is easy for you or modeling a 3D is easy for you. Modeling is 2D very simple for you. So you can proceed your analysis easily and you can complete your analysis actually. Okay. Now let us see the plane stress first. Okay. We will see plane stress first. Okay. So if it is a plane stress, the thickness, okay, the thickness of your object should be very, very small. Okay, you see that for plane stress, thickness should be very less than the length and breadth. Normally thin walled plates, okay, thin plates, you see that thin plates comes under this category. And this load is actually called in-plane load. This load is actually called in-plane load. Okay, so I just take a paper. Okay, so this is you just imagine this is a 2D object. Okay, so this is a 2D object is our intelligent assumption. Really, it is a 3D. It's having a micron thickness, correct? The moment you talk about thickness, it becomes 3D. Okay, it's a small thickness, but it's a small thickness. Okay, now what's the meaning of in-plane load? The meaning of in-plane load is this is called in-plane load. Okay, this is called applying this kind of load is called in-plane load. Okay, you can imagine this this paper is a very thinnest object. What is this paper? It's having it's not at all having any strength. It's a very weaker object. You can imagine. No, it's very stronger in in-plane direction. You can check. You can apply a load now. Okay, try to tear this paper. If you tear this paper along thickness direction, it's a very easy job for you. Okay, now if you want to tear this paper along this in-plane direction, it's very toughest job for you. It is very toughest job for you. Correct? It is very tough. So the in-plane strength is very higher. The in-plane strength is very higher. Okay. So such objects, the object having small thickness, okay, comes under this category. Now you have a plate with hole. So just a minute. You just take 2 minutes break. Hey, Vignesh, என்ன பாட்டு கேக்குது? யார்? சொல்லிடுறியா ஆன்லைன் போய்? சொல்லிடுறியா? சரி ஆன்லைன். சாரி. Okay, so if you have a plate with hole, okay, so the length and breadth If you compare the thickness, okay, the thickness is very smaller if you consider the length and breadth. So you can neglect the thickness direction. This is the solved example. Okay, you are seeing the stress concentration occurring here. Okay, so you can have a brackets, you can have a spanner. Okay, you can have any mechanical components having less thickness. So no need to model it as a 3-dimension. You can simply model as a 2-dimension. For components like this plate with hole, there is one more opportunity for you. It's not that you can model a full model. You can also go for a half model. You can also go for a 1/4 model. You can also have a 1/4 model, and you can simplify your results. You just see that you are solving a full model, you are solving 1/4 model. You compare the computation time, it is very easy for you. Okay. So this comes under plane stress. So most of the automotive components, okay, for this an example of a rectangular L bracket comes under this plane stress. So no need to model the thickness. Okay. For plane strain, okay, for plane strain, here also you can convert it into 2-dimension. In the very first slide, title slide, you are able to see a dam sketch, correct? This is a dam sketch. Okay, now I want to solve for this structure. This structure is subjected to water pressure. Okay, for this, what is the assumption here to convert 3D into 2D? 3D into 2D. Okay, so if you have a long prismatic object, okay, what is prismatic? The cross section will be same throughout the length. That is called prismatic object. Okay, if your object is very long and prismatic, you can take a slice of it. You can take a cut section instead of this total 3D object. You can take a cut section. You can take a cut section, and you can model that 2D alone, and you can get the result. Okay, because so the assumption in the previous analysis is stress. You have to think about why we are neglecting the thickness direction. That is very important. There should be a reason, no? There should be a technical reason for neglecting the thickness direction. That reason is nothing but across thickness direction, stress is 0. Okay? Across thickness direction, stress is 0. So we simply neglect the thickness direction. Now coming to the intelligent assumption here. This is a very larger massive structure. So strain along this axis will be 0. Already it is a massive structure. It's a very long structure. So strain will be 0 along the length of this component. Okay. So that's why it's named as plane strain problem. Okay. Now with the example, you can see that. I think you are able to see easily. It's a very long dam structure. So the correct analysis of the dam, instead of making a complete 3D model, you can take a cut section. You can simply take a cut section like this, and you can convert it into a 2-dimension. I think the next slide you will get the idea. Correct. This is the post-process results of a dam. Okay. I just modeled this as a 2-dimension. Okay. And the assumption here is the results, okay, these results are applicable at any point of interest, provided you assume the water pressure as UDL, uniform. Okay, this is the plane strain. There are many examples. You consider a tunnel. Okay, this is a tunnel structure. Like a tunnel structure, you can model it as a plane strain. Wherever very larger component, massive structures are there, you can simply take a slice of it and solve it. That is called plane strain. Okay. Now coming to the point of axisymmetry. So axisymmetry, we studied in detail. All the students have studied in detail the solids of revolution. Even in engineering drawing. Okay. You can see here how you generate a cylinder. If you revolve a rectangular with vertical edges as fixed and you rotate 360 degree, you will get a cylinder. Okay. How a cone is generated? If you revolve a triangle, right-angled triangle about vertical fixed, you will get a cone. Okay. How you get a sphere? If you revolve a semicircle with vertical edges fixed, you will get a sphere. How you get a hemisphere? If you revolve a quadrant, of a circular plate, you will get a hemisphere. These are the solids of revolution. Okay. Now, if any structure is having axis symmetry feature, the very best example is the entire rocket structure. I hope the model is visible, Gerald.
Sir, visible, sir.
Okay. So you just see this rocket structure. So this is a model of a rocket. This structure comes under axis symmetry. You just imagine this as axis. You have an axis. If you draw an axis throughout the rocket, okay, you will have an axis symmetry. So how this axis symmetry is coming into the picture? You just imagine a combination of cylinder, over that a frustrum of cone, over that a hemisphere, over that a hemisphere. So combination of cylinder, over that, so you have a frustrum of cone, over that you have a hemisphere. Okay, so instead of modeling the rocket as an entire 3-dimension, you can convert it into 2-dimension. Okay, so many examples are there. All the pressure vessels comes under this axis symmetry. Okay, so what I will be doing, so I will be simply modeling like this. Okay, this is a cylindrical tank, okay, or pressure vessel. I don't want to model the entire tank. This comes under axis symmetry. So you can simply model it as a 2D. Okay, this is the axis symmetry. So wherever, and you can mesh the 2D and you get the result. These results are applicable for, let's say example, if you are taking this cylindrical pressure vessel problem, you are modeling only a rectangle, then you mesh it and solve it. That answer is applicable for any radial section, that is across theta direction, stresses do not vary. So the technical assumption in plane stress is across thickness direction, stress is 0. The technical assumption for plane strain is across thickness direction, strain is 0. The technical assumption in axis symmetry is across theta direction, stress do not vary. You have to understand this intelligent points, technical points clearly. Then only you will be able to use all these features in your ANSYS modeling. Okay. So some of the examples are cooling towers. You just think about a cooling tower. Okay, correct? So it comes under axis symmetry. So I don't want to model the actual entire 3D. You can go for a 2D like this and you can solve it. Okay. Yes, this is what now I explained for axis symmetry rocket vehicle structure. But this is actually 3D. This is the 3D analysis. Okay. Many of the this is called space capsule recovery experiment. Okay, these are the space capsule. So this capsule also comes under this axis symmetry feature. So for modeling this thin-walled shell, you can simply model a structure like this, and you can use it use the axis symmetry structure. Okay, this is a human space system. Okay, now India is working towards this human space flight. Okay. So for this, they will be having a crew model. This crew model also comes under this axis symmetry. Okay. Yeah, of course, all the thin-walled shells are used in aircraft applications. Okay. So you just see this is a radome. Okay. You have a radome. You are able to see a nose cone in the flight. This nose cone is called a radome. Radome is nothing but radar plus dome structure. That is radome. So if you can consider this radome, that is coming under this axisymmetric structure. Now, suppose if I am considering the entire fuselage, I think in some of the slide I show you the fuselage structure. I'll go to that slide. Okay. Yes, you see the fuselage here. Okay, you see the fuselage. Okay, so the fuselage is a long structure. Okay, the fuselage is a long structure. It is not that I have to model the complete fuselage. You can take a slice of it and you can solve it. Okay, that is enough. Okay. Now coming to the point of next topic, a simplification of order. So you have to clearly understand the simplification afforded in your structure, which you are going to model in CATIA or Pro-E or SolidWorks. Okay. First one is planar symmetry. Planar symmetry is nothing but, okay, the plate with hole problem I have explained, correct? You have a plate with hole that is having planar symmetry. We'll see an example. So this is what I explained. Okay, just now I explained this concept only. You have a plate with the hole. So the full model is not essential for modeling. I just take half of the model. You see the magnitude of the result, the same result will be applicable here. Still, I make a simplification. I just model 1/4 of the model. Then also the same result is coming. Then why it is required for modeling the entire structure? That's the advantage of planar symmetry. Next comes cyclic symmetry. Cyclic symmetry, all the wind turbine blades comes under cyclic symmetry. You have wind turbine blades in many types of prime movers. It may be a steam turbine, maybe a you have a wind turbine, gas turbine. Okay, you know the gas turbine. You see that the gas turbine. This is an example. This is a result of a gas turbine blade. Okay, you are seeing this many blades are arranged in some particular angle of difference. Okay, and for even hydraulic turbines. Okay, so all these prime movers, if you are want to model in softwares, especially you have to think about CFD, correct? The moment you talk about fluid, all these prime movers are concerning with fluids, flow of air or flow of water or flow of steam or flow of hot gases, correct? So whenever you model such problem, you have to concentrate on CFT, computational fluid dynamics problem. Okay, but however, either for FA or CFD, the pre-processor is same. Pre-processing is nothing but modeling of the object is same. Okay, so at the stage of modeling, you have to consider this cyclic symmetry. Okay, if you are modeling turbine problem, simply model one turbine and get the results and you can conclude it. Okay, similarly for wind turbines. Next is repetitive symmetry. Repetitive symmetry will occur in many long structures. Repetitive symmetry will occur in many long structures, many prismatic structures. Okay, so you might heard about infinite body. I can give some examples for infinite body. A ship is an infinite body. Aircraft is an infinite body. Why not? You want to model a sea. You want to model a ocean. A ocean is an infinite body. Correct. So a train is an infinite body, a very long structure. For modeling such problem, you have to consider repetitive symmetry. So you are modeling a train car body. Okay. Even it's not required to model the complete compartment or complete train. You can simply take a slice of a train, and you can solve it. That's what I explained in aircraft fuselage. In aircraft fuselage, it's a very long structure made out of, actually really there are three parts rigidly joined together to form a fuselage, and it's made out of glass fiber reinforced plastic. You want to solve this by analysis. It's not that you have to solve the entire fuselage. Simply take a slice of it because it has a repetitive symmetry. Okay, rack and pinion. If we are seeing rack and pinion, you just see the shape of a rack. It's a very long structure. You can use the rack. Okay, why not for conveyor? We are seeing conveyor in many applications. You can see in all the cement factories, okay, all the textile mill or process industries, even in airports. Okay, even for a good transportation, we are seeing these conveyors. So conveyors have the linkages, same type of linkages are there. You can apply this repetitive symmetry for all the steel framed structure. Repetitive symmetry is applicable. And why not for constructions like arches, bridges? This kind of repetitive symmetry is applicable. You can simply take analyze one arch and you can conclude your results. So up to this you are seeing the applications. And in terms of equations, so plane stress, plane strain, we have to think about equation that will be in the second material as PDF. So I will share the PDF. So Gerald, I am just closing this.
Yes,
Okay,
sir.
sharing.
Yes, sir.
I am sharing.
Okay, sir.
I would like to share the PDF, and at
Okay, sir.
last we will have the discussion. Okay, at last we
Okay,
will
sir.
have the see that 61 participants are attending.
Yes, sir. Yes, sir.
Gerald, how to? Yeah, I got the material. PDF.
Sir. Present now again entire screen, sir.
Is it visible?
Visible, sir.
Okay. So
Full screen mode, sir.
it is
Full
very
screen.
easy to understand. Students, you can see the plane stress and plane strain here. It's a very simple sketch
Sir,
for plane stress. This is the
sorry for the
simple
interruption,
sketch.
sir.
Yes,
Sir,
yes.
you change it as a full screen mode, sir. View full screen, sir.
View full screen.
Control L or Control L. You press Control
Control.
L.
Okay.
Yes.
Okay.
Yes, sir. Clear, sir.
Is it okay?
Okay, sir. Just to
Okay.
zoom in, sir.
Yes.
Zoom in, sir. Control scroll. Yes.
Okay. I will zoom it.
Yes, sir. Now okay. Now okay.
Okay. Sorry for the inconvenience caused. So
No,
for
no.
plane stress and plane strain. Okay. So this is a 2D object. This is a 3D object. So I say this is the plate with small thickness. Remember, plane stress is applicable only for small thickness. Plane strain is applicable for long prismatic object. Okay. So dimension thickness is very less than length and breadth. Here, the thickness is very larger than length and breadth. Okay. Now you see what type of loads are there. I demonstrated in-plane load for plane stress. Okay. So here in-plane load. For plane strain, it is subjected to perpendicular load. That is transverse loads. Because we talk about UDL. Okay. You have seen the image of the dam. Is the dam and the water pressure are acting like this, perpendicular to the dam. So that is called the transverse load, or that is called the bending load. Okay. Now coming to the terms of equations here, it's very easy to understand. No need to mug up anything in FEA. If you understand the principles, you can easily write the equations. So here I say that the stresses sigma z, tau zx, tau zy is 0 at any point of interest. Now, so I say that you are able to see this paper. Okay, you are able to see this paper. Okay. So suppose if I put any object here, this paper is easily deforming. It is easily deforming. Okay. If you want to tear the paper, you can easily tear the paper. Why you are doing easily? Because stress is 0 across the thickness. Across the thickness direction, stress is 0. So what is Z? Z is coming under thickness direction. So the stresses related with the Z direction, that is thickness direction, is 0. So sigma zz, tau zx, tau zy is 0. Okay. Now coming to the point of here, you say that it's a very long structure. Very long structure. So for very long structure across thickness direction, there will not be any strain. Okay, because already it's a massive structure. So the strain along Z direction, that is sigma zz, gamma xz, gamma yz is 0. What is non-zero stress component? Sigma xx, sigma yy, tau xy is not 0. That is, these three stress components exist. That is called plane stress. Okay. I just demonstrate this. If you apply a load like this, the paper is not tearing out. The paper is not failing. Why? Because the moment you stretch like this, stresses are flowing. That is sigma xx is present, sigma yy is present, tau xy is present. That is why you are not able to tear this paper. Okay. So the stress related with x and y, that is sigma xx, sigma yy, tau xy is present here. Then here non-zero strain components. Okay. Here also strain will exist only along xx, yy, gamma xy, which are not 0. Okay. This is generally known as 2D state of stress. This is generally known as 2D state of strain. These are the tensors. See, tensors, we use this notation in FEA, okay, to represent stress and strain. And if you see the stress strain relation, this is what I am interested. My last discussion is about this. Stress strain relation. Okay. We will see the stress strain relation for 2 dimension. Okay. For 2 dimension. So for this derivation, we assume that the material is isotropic, homogeneous, linearly elastic. Okay. Homogeneous, it's made out of same material and you don't have any voids present. Okay. Isotropic, the meaning for isotropic is, so the Young's modulus, you say that the Young's modulus for steel is same, correct? You say that Young's modulus for steel is same, that is at any point, that is called isotropic. Suppose if you say the Young's modulus for composite material, you cannot say it as isotropic. That comes under orthotropic. Okay. Then what is linearly elastic? Linear in the sense there is a linear response between stress and strain. There is a linear response between load and deflection. What is elastic? It's a property of elasticity. Okay. Then deformations are very small, rotations are very small. This is a very important assumptions and objective in FEA. Even in strength of material, see for FEA, strength of material is a very prerequisite knowledge. Of course, engineering mechanics. Strength of materials are the prerequisite knowledge for finite element analysis and ANSYS laboratory. Okay. So if you why these deformations are need to be small, you just think about that. In strength of material, we have a beams. Okay, we have beam problems, simply supported beam or cantilever beam. Okay, and you are calculating using some analytical y max equal to theta max equal to. All the answer you can see that it will be very very small only. So y will be in 0.001 millimeter or meter, something like that. Okay. So your deflection should be very, very small, or else what will happen? So the object will fail. That goes to plasticity. You just see a crashing of a bridge, collapsing of a building. That comes under plasticity problem. You just think about crashing of automobile. That comes under plasticity problem. In plasticity problem, deformations are larger, rotations are larger. Okay, you are considering a bridge. The vehicles are running, dynamic load is acting. That load will create a deflection in every bridges. That will be in terms of very small 0.001 millimeter, something like that only. Okay. If you are saying that your rotation, you say that, sir, I have designed a bridge. And with rotations as 60 degree or 70 degree, then that is a joke. Okay. Then nobody will buy the design. You have your rotations, larger rotation in the sense it is failing, larger deformation in the sense it's failing. But that is why we use FEA. That's why we are using FEA. We ensure that the deflections are very small before producing the product. Okay, you ensure your rotations, your deformations are small so that you can exhibit safety to the users. Okay. Now you are just taking a, see, normally in strength of material we just draw a square like this. Nobody know why we are drawing a square. Okay, this is not a square, actually this is a dot. You just take a point in an object and you are giving a shape to an object. The shape you are giving as a square of dimension dx, negligible dimension. And for 2 dimension, there are 3 stresses exist: sigma xx, sigma yy, tau xz. That just now we discussed. Okay. Now I am splitting into 2. Okay. One is I am considering sigma x. Other one I am considering sigma y. Other one I am considering shear. This is called a pure state of shear. Okay. The dotted line shows is the deformed shape. Okay. Now for these 3, you are superimposing this into 3. Only for linear problem, that is for smaller deformation problem. For plasticity, you cannot do it. Okay. Now I am simply using the Hooke's law, sigma equal to E into epsilon. By using the formula, I am writing epsilon x equal to sigma xx by E. See, for all these 3 cases, what is the sigma x, sigma y, gamma xy value I am writing. Okay. You see that's epsilon yy equal to y. I am using minus sign here. The minus sign here is you are pulling the object like this. So elongation will be along x direction. Contraction will be along y direction. That you have to indicate in your equation. That's why minus n is coming. Along with that, you have to consider Poisson's effect. Okay. This Poisson ratio is investigated by a great mathematician named Poisson. That's why we are using Poisson ratio here. Okay. So minus nu sigma xx by E. Why we put gamma xy 0? Here there is no effect of shear here and here. So 0 and 0. Why we put sigma xx, sigma yy 0 here? Here there is no effect of linear strains, only shear strain. Okay. Now coming to sigma yy, you apply load like this. So along y direction, your deformation increase, and along x direction it contract. So along x direction minus nu sigma yy by e. Okay, here you'll get sigma y is, sorry, epsilon yy sigma y by e. Okay, and here only gamma xy exists. That's the relation between gamma and tau. So shear strain equal to shear stress by G. G is the modulus of, so shear modulus. Okay, G is the shear modulus. Okay, now I am going to add it, these three components. I just add it. Okay, see that simply I am adding along epsilon, all the epsilon x's, this one, and this one I have added. Then all the epsilon yy, this one, and this one. Then all the epsilon x's I just add it, and I am adding and simplifying. Okay, so if you put it in matrix form, now I put it in matrix form, epsilon xx equal to, I just take a 3 cross 3 matrix here, then you will have a stress here. But normally we need stress strain relation, not strain stress relation, stress strain relation. So I put, I just change the sign here. I just change the sense of writing. So sigma stress in terms of strain, you will get this inverse matrix. By applying 3 cross 3 inverse matrix, you will get this answer. So this is called constitutive equation. There are other names for this. This is called stress strain equation, constitutive equation. Okay, and this is called elasticity matrix. And this is applicable for plane stress. Remember, this is applicable for plane stress. Okay, so up to this, I will end my session, and I will be happy if you discuss. Okay, I think you have some 10 minutes.
Thank you, sir.
Stop sharing here.
Yes, sir.
I'll be happy if you discuss with me. I'm happy to see my PhD scholars are also present here. It's good. And Gerald, I think during your introductory section, you wrongly mentioned that you studied only FE under my guidance. I think you studied many subjects under my guidance: engineering graphics, engineering mechanics, strength of material, and SysLab. Am I correct?
Yes, sir. Yes, sir. Yes, sir.
I think you forget. I don't know whether you forget this or not.
No,
Okay.
sir. I related this topic, sir. Finally,
No problem. So if your student or if your colleague have any question, you can discuss. I'm happy to discuss with you.
Yes, participants, if you have any specific questions, you ask directly by unmuting the mic. Otherwise, you can post your questions in chat box, and
you can also give my mail ID to the participants. You can also forward.
Yes,
suppose if they can mail for any complex problem, if they want to contact, they can contact me over mail also. Okay.
Yes, sir. Yes, sir.
See, all are your final year students. These students are your final year students.
No, sir. All are outside participants, sir. Faculty members.
Oh, all are outside participants.
Yes, sir. Yes, sir. Majority outside participants. Sir.
Oh, great. Okay.
One participant from Indonesia, sir.
No problem. Okay. And kindly convey my thanks to your HOD Rajapalayam sir and all the coordinators for providing me an opportunity to share.
Yes,
okay.
Yes, sir. Yes, sir.
Now, Naveen sir, do you have any question? I hope you understand, Naveen, about convergence. And one point also I forgot to inform, whenever you write a paper or write your thesis in FEA, you have to include a chapter called verification and validation. Okay, verification and validation. Verify your own result by using convergence. If you complete convergence, that is verified. Okay. So by performing convergence, you can verify your results whether it is correct or wrong. Okay. You will feel convergence once you slowly increase the number of element or slowly decreasing the number of size of mesh. At one point, your results will not improve further. Okay, that situation have to occur in your analysis. That is called verification. Then what is called validation? Your results you have to validate with the outside world results. The outside world have to accept your result. Okay, how this will happen? Definitely you can compare with your results with others' work, others' literatures. Okay, literature's test data or your experimental results. Okay, and you can validate your results. So convergence, verification, validations are these three categories are very important for all the researchers in your paperwork. Okay.
Yes, sir. Yes, sir. This is Naveen, and
Yes. Yes, sir. Please, please.
I thanks Professor Nathan, sir.
Sir, it's. I think your audio is not clear to me. Hello.
Now it's okay, sir.
Yeah. Please, sir.
Yeah, I thank you, sir, for giving a refresher.
Yeah. Thanks.
However, it's like a very good introduction session for us to know once again to go through the plane stress, plane strain problems and how to form the constitutive equation.
Yes.
So,
Because people will not understand the problem initially. They will directly model it as 3D. That is not required. That's what my objective. Okay. Yes.
correct, sir.
Thanks,
Yeah.
sir. Thanks.
Thank you, sir.
Sir, from the participant side, there is a 2 questions, sir.
Yeah.
First question, sir, can you tell me some FA book author names? One participant asked,
good. So actually, I am following author. My guide in IIT. My guide named J. Ramachandran. There is a book called Boundary Element and Finite Element Method. I request all the participants to note down this book. Nobody will use it because they will not know the title of the book. The book starts with Boundary Element and Finite Element. The author name is J. Ramachandran. Okay, this is a very good book for beginners also. Okay, so I studied finite element based upon that book only. Okay.
Sir, one more question, sir.
Please.
Mr. Aryan asked about the in-plane strain problem. Strain
Which
across
problem?
length is in-strain problem, sir. In-plane strain problem.
In plane strain.
Strain across length is 0. What about the stress value, sir?
Yeah. Actually, so we discussed, So we actually take, you consider this object. So it's a very long prismatic object. By applying loads, it is not that your length of the object will extend or contract. So strain is 0 actually. Okay, it comes under plane strain problem, and you just take a slice of it. And in that slice, you will be finding the strain value. Okay, so stresses also you can plot it. Okay, these assumptions are applicable for reducing the geometry. But after you simplify it, definitely stress plot you can plot it. Okay, so I think I have shown a dam problem, correct? In that also, that's a stress plot. Okay, you can plot the stress for the element.
Okay, sir.
Any other?
No, sir.
Yeah, thanks again. Okay, I thank you everyone for sparing your.
Hello.
Yeah.
Sir, this is Amudan, sir. I'm also a student.
Tell me, Amudan. Tell me.
I like to register something, sir. We are having hands-on session every evening, sir. And I like to say to the participants that Dr.A.Vasanthanathan is one who introduced ANSYS to me. And after 3 years, now we are able to solve all the strength of materials problems in R.K. Bansal book in the session during the evening session. He is the one who introduced ANSYS, and he has handled finite element analysis for me. He is the one motivation behind validation and
it is very important. Yes.
Thank you, sir. Thank you.
Yeah, thanks, Amudan. Okay, Gerald, can I quit the meeting?
Sir, in participant side, so all are having good.
Okay. If anybody would like to contact me over mail, please kindly give my email ID and they can discuss with me. Suppose for their project work, for their PhD or research, if anybody would like to discuss with me, you can forward to me also. Okay, I am interested to help them. Correct?
Yes, sir. Now I invite Dr.A.Vasanthanathan sir to.
Yeah. So actually, from 4 o'clock, I have one more work. I need to go to that department. That's right. Okay, I'm not able to continue for further discussion. Thanks again. Convey my regards to your HOD. Okay.
Just 2 minutes, sir. Sukma sir will give the vote of thanks.
Pardon?
Just 2 minutes. Dr. V. Sukma sir giving vote of thanks, sir, about that.
Oh, please. Yeah. Please. I will wait.
Good evening to all. on behalf of Ramco Institute of Technology Management, Vice Principal, Principal, and Department of Mechanical Engineering, faculty members, it's my immense pleasure to register my sincere thanks to our chief guest. So
Yes, sir.
thank you very much for your valuable sharing, sir. So the
Thank you.
students,
Thank you,
definitely, faculty members, student community, and definitely they will get a lot more benefit from your insights about finite elements, sir. Thank you very
Okay.
much for your valuable sharing, sir. So you have addressed about the difference between the plane stress, plane strain, axisymmetry, and you have given some live examples about
Yes.
given discuss about the dam chimney with the help of this. You just make a clear concept definitions to our participants on behalf of the Department of Mechanical Engineering, especially faculty coordinator Gerald John Bitto and his team Prabhakaran and Amudan. I am very happy to give a thanking to your most valuable talk in this webinar, sir. Thank you very much. Thank you all the participants. Thank you for
Okay.
your.
Yeah. Thanks, Kumar. Thank you very much. Thank you. And in the chat window, I am able to see some questions. If I have not answered any question, please forward all the questions to me, Gerald. Okay.
Yes, sir. Yes, sir. Yes, sir. Okay, sir. Okay, sir.
So that I can reply via mail. Okay.
Yes, sir. Yes, sir. Sure,
Yes.
sir.
Yeah. Thank you. Thank you very much.
Thank you, sir. Thank you very much, sir.
Thank you. Thank you again.
Yes, sir.
Participants, the current session's link only will be sent through the chat box. If you are not able to fill it, please attend the other sessions regularly. Please don't ask for the completed sessions link. It will be closed. The link will be active for 10 minutes. So please try to complete it within it. So it will not be sent to your mail ID and all. It will be sent only in the chat box during the session.
Yes, once again, I posted the feedback link. You can use it, participant. Yes, Amudan sir, what about today's session, sir?
It was nice, sir.
Okay.
I think sir is a little bit busy.
Yes.
So,
We're going for auditing, sir.
Okay.
Hello.
Yes, sir. Sanjeev, sir.
I'm streaming in the morning. I'm streaming YouTube. I missed the feedback link. You can check that there. I stream YouTube.
Yes, sir. No problem, sir. You sent your request in WhatsApp group, sir. So we will reply on that. You can give your feedback, sir.